Today we have to talk about invariance. Invariance is a crucial subject in physics, in mechanics. In this period I am crazy about Piola. I spent yesterday and the day before yesterday, among other things, in the Istituto Lombardo per le Scienze e Arti, where I found all manuscripts of Piola about also this subject. Invariance, rephrasing Piola, means different observers must verify, must check, experiment the same law of physics. However, when you write down the equation of motion, you write tensors and vectors in terms of components in a given basis. So I propose you to start once more from the scratch. So we consider, I need to draw something. The orthodoxy represented, for instance, by the ideas of Professor Di Carlo is that somebody should never draw a reference frame, because this is, your hands become dirty because you have drawn a reference frame. I think that this is only partially true. So if you consider a reference frame, you can attach to a given vector in three-dimensional Euclidean space, to a given vector you can attach three numbers, and these numbers are the components of this vector. The rule with which you write this representation we have already seen, but it is better if we repeat it here. So VI are scalars. You multiply E1, E2, and E3 times this scalar, and you get the vector V. Mathematically speaking, a vector in this context is the mathematical object modeling a displacement or a velocity. Real numbers are much more general, are a kind of joker you can play whenever a quantity is involved. You measure with real numbers forces, weights, volumes, everything. Okay, so you should be very suspicious if, when talking about vectors, somebody tries to tell you that actually vectors are triples of numbers, because there is not enough structure in the model for telling you what you really need. So let's do another step. I hope that you will, if I tell you things like I've read this in Feynman, you go and read it. Okay. What I'm telling you, you can read nearly word by word in lecture, Feynman's lectures in physics.
Maybe even the five in Italian is 5 pezzi facili.
No. You know, my age, I studied physics first and second year on Feynman's lectures. This should be in the first volume. There is a volume with Italian on the left and English on the right. Very, very comfortable, very useful.
You should try to read these things. I mean, this book by Feynman, they give you an overview of physics, which
you can select. Yeah, you can select the subject. Sometimes nobody is so clever, even Feynman, to be able to tell everything in the best possible way. So there are some weak, fake moves here and there, but the ideas are very good.
Puoi passare dopo un attimo.
Sì. Okay. So in this context, the ideas are very good. So let's move another step. Instead of having E1, E2, and E3, I can choose another triple of vectors. I have drawn them being orthonormal, but this is not essential in this representation formula. So the same arrow, so we could say that displacements are set of displacements is a set of arrows. Of course, this means nothing. Okay, but keep in mind the geometrical object. Okay, you change. I should draw the same, the new reference frame with the same origin, but the drawing could become a total mess. So I have E prime 1, E prime 2, E prime 3, okay, and I have the particular property that every prime vector can be represented in terms of linear combination of the non-prime vectors. I'm sure that you have studied the abstract setting of vector spaces. A basis in a vector space is a set of linear independent vectors such that every vector, included the zero vector, can be represented in a unique way in terms of linear combinations of the basis of the set of vectors forming the basis. Okay. So using Levi-Civita formalism and using the trick of calling the index with the prime instead of using the prime with the letter, which is very useful for doing calculations. So when I write Vi prime, Ei prime, I mean that I'm considering E prime 1, E prime 2, E prime 3. Okay? I don't tell anything about VE prime because these components mean anything. It doesn't mean anything if you don't specify which is the basis. A set of components is meaningless if you don't say which are the vectors of the basis. Okay? So the same displacement can be represented in two different ways, simply changing the basis. But as Feynman underlines, they are the same objects. V represented by the first equality and V represented by the second equality is the same object. Of course, I don't like the philosophy of science of Feynman, which is mixing mathematics and physics. So when he talks about velocity, he is not able to say anything without telling velocity, for instance. Okay, this animal could be force, displacement, everything which is which needs to be regarded as a vector. Okay. Now, what I've discovered recently, I like to tell this because it is beautiful. The poor Piola started to understand this structure when, being only 56, died and left to his pupil to complete his paper. The pupil simply published the pages written by Piola and he didn't complete the work. So you see the pencil falling down and you see one chapter cut in one part. He had introduced a denotation which was precurring this one. Why? Exactly for what we need to understand now. We need to understand if I give a constitutive equation in terms of vi or vi prime. So if I introduce a function which tells me something starting from the vector v, which is a consequence of the vector v, okay, of course, if this function must appear in a law of physics, this function should not depend on the particular reference frame in which I'm writing it. It has to be independent of the chosen reference frame. Okay, so this is our delicate point now. We have to understand how to write laws in terms of components, but these laws must give the same result in every reference, with respect to every observer. Okay, so let us call, as we did already, Qi I prime E I these are the components of the matrix which is transforming the basis EI into the basis EI prime. This is the first time when we need a mathematical object with two indices. Why? Because you need to sum up over E1, E2, and E3, but you have three vectors at the end of the story. So, of course, you can do like, okay, when Cauchy did the first time, wrote the first time such a representation, he wrote it in this way: A, B, C, D, E, F, G, H, I. He wrote here E prime 1, E prime 2, E prime 3 equal, and you have the rule row times columns, and you, oh, of course I changed, so E1, E2, E3, and here you have E1 prime, E1 prime 2, E prime 3. Okay. So, why your colleague who is, sorry, I need somebody with whom to talk. Your colleague who is complaining all the time could tell me why you are obliging us to understand this twisted notation while you could have written the other way, and you should not explain me anything. Okay? The problem is that you have asymmetry in these formulas. You can rename E1, E2, E2, E1, and the structure of your formula is not changing. However, A, B, C, D, D, A, F, and G, H, I are changing. So you need to write your formulas in such a way that a meaningless renaming of the basis is not causing any disruptive change of the structure of your formula. Okay? Now the poor Piola invented a first step just before dying. He invented this notation: tau 1, tau 2, tau 3, sigma 1, sigma 2, sigma 3, rho 1, rho 2, rho 3, which is already a step towards the final Levi-Civita-Ricci formula. Okay? So, this formula with included Einstein summation rule is a very powerful abstraction which gives you a powerful tool for investigating nature, because in this formula you are not distracted by useless and irrelevant details. In this story there is no relevance about the position in a row or in a column if you permute the names of the vectors. What is important, and this is written very elegantly in this formula, what is really important is that you could translate in natural language this formula in this way. Every vector of the prime basis is a linear combination of all vectors of the non-primed basis, which is much longer. By the way, Piola wrote every formula, and under this formula writes in Italian the translation of the meaning of this formula. This was the habit of the age. Okay? Okay, now we do another step. As I want to exert a captatio benevolentiae, I want to please Professor Casciola, so I choose an example from fluid dynamics. Okay? So, the vector field we are talking about could be the velocity field V. Okay? We are lazy, we immediately choose a reference. Okay? And then we understand that viscosity depends on the, viscosity is a word I dislike. The quantity of dissipated energy depends on the gradient of velocity field, on the Eulerian gradient of velocity field. Okay? So what is dissipating energy is the relative velocity of two close particles, very close particles. Okay? So you are, and I'm sure that everybody among you agrees that this animal is the right animal. Of course, I hope that you understand what a partial derivative is. Okay? So, this is the candidate for being, of course here I have defined the velocity field deriving the placement, and then I have transported it in the Eulerian configuration. So this V has to be regarded as an Eulerian field. So I derive with respect to small indices. Okay? Now I want to write a meaningful formula expressing the dissipation related in a given point related to this quantity. Okay? So this is exactly what you find in the papers by Navier, Stokes, and people discussing this subject. Okay, so I have integral over the Eulerian volume of a density of dissipated energy, okay, which is a scalar, integrated over the Eulerian volume. So we claim that the physical mechanism which is under the dissipation energy okay, the dissipation of energy in the flow of a fluid, okay, can be modeled in terms of density of dissipated energy per unit volume. This is not true always. Think about phase transition, Laplace laws and things. But for describing the motion of air around a wing, this model is suitable. So we can imagine to have a class of dissipation mechanisms which are governed by this animal. Now we are like Stokes. The dissipation energy is a function of these numbers, Vi, j. Okay. Now, dear friends, can we imagine a theory in which two different observers measure a different dissipated energy? So it is clear that here you have a redundant representation of this gradient of velocity. You have too many numbers running all around you, and all these numbers are not all independently needed for describing the dissipated energy. You need to distillate, filter, select some other numbers from these numbers to get those which are really governing dissipation in this phenomena. So the driving guide was, I need to postulate this constitutive equation for dissipated energy in such a way that it is invariant with respect to change of observer. Now you understand why I wrote you this formula on the other side. Because what I need to do is to write a constitutive equation epsilon d, okay, such that epsilon d Vij is equal to epsilon d Vi prime comma J prime. So I cannot give a constitutive equation whatsoever. I must choose a constitutive equation in such a way that when I change the observer, so when I change in the correct way the components of V and the components of grad, the operator of derivation, these two quantities are the same. Of course, I have not written something very important. I must change the observer in such a way that lengths are the same. So I need an orthogonal matrix Qij. Okay? You can read this written in Italian in the book of Piola. What is astonishing is nobody among the several thousand mechanicians whose mother language is Italian, nobody remarked this. It was at page 220, so nobody arrived there. I strongly suspect. Okay? Okay, now we go back to Feynman. The mathematicians, and you hated mathematicians, I'm sure, okay, came to you one morning and they said, I call a vector space a set endowed with an algebraic structure. I have a set of objects. Let us call them arrows in physics, in mechanics. Then I have a set of scalars, real numbers. Then I have a sum. Then I have multiplication times a scalar. And I have 11 properties. I call a vector space a set with these algebraic operations and this set of scalars. Everything which is defined verifying these properties is a vector space. I have a sequence of students coming to me and asking me about the metaphysical meaning of the word vector. There is no metaphysical meaning of the word vector, neither physical nor metaphysical. This is the definition of the word vector. Okay? You are allowed to talk, to use the word vector if you have a set V whatsoever, a set of scalar, a sum, a product, and you are defining suitable operations on this set of objects. Feynman. In my opinion, Feynman is here more twisted than mathematicians. Do you know how Feynman calls a vector? What Feynman calls a vector? A vector is a class of equivalence. Is the class of all components which transform one into the other with the rule of contravariant rule. So Feynman takes R3, the set of tribal of real numbers, okay? Then he takes E1, E2, E3, one basis. Then he takes all bases, B1, B2, B3, the set of all bases. To every basis, he is associating V1, V2, V3. V prime 1, V prime 2, V prime 3. Okay? Then, if these numbers are transformed into this number with the same rule, which is transforming this vector basis into this vector basis, be careful with contravariant and covariant rule, then it tells that this and that are equivalent and represent the same vector. He starts a wonderful discussion about this entity which tries to escape you, but you trap it with its transformation rules. Okay? So for him, a vector quantity, a physical vector quantity, is something to which every observer associates three numbers. And how the observers recognize that they are talking about the same quantity? Because the coordinates, the components in one reference are transforming in a given way in the components of the other reference. These two approaches are completely equivalent. This one you can teach in less words and, more important, without using too many of these transformation formulas. So it is for this reason that mathematicians are obliging you to this abstraction.
I think maybe it was Heisenberg rather than Feynman doing that.
No, I think that the true guilty of this is Levi-Civita himself. And as you know, Levi-Civita was producing two traditions. The tradition of mathematicians and the tradition of theoretical physics. I think that via the book he wrote in English, Heisenberg learned about this and then used systematically. In France, Lichnerowitz did it. In the United States, they were imported by the Jewish German escaping there. So I'm nearly sure that this point of view is Levi-Civita, the original one by Levi-Civita. And this is the re-elaboration of modern abstract algebra of the same subject. Okay, so you may believe that I'm a little bit schizophrenic, I'm not talking about the same subject. This is not true, because you are accustomed to this symbol, grad V. Okay, but how they introduced it to you? Also, this bad boy. Okay? People are telling you, take a reference, represent the vector V in components. I'm sure that Professor Asciola is telling you orthonormal reference, because otherwise it can be dangerous, but there are people who are not telling this. Okay? Then calculate partial derivatives, you have the components of grad V. Of course, somebody could ask to these people, okay, and if the observer is another one, I get other numbers. So you are talking about a gradient of velocity, but what it means? Okay, now I give you the definition by Levi-Civita, I give you the definition by abstract algebra, we verify they are the same, so we give what can be called intrinsic or absolute meaning of grad V. Okay? So one could do, and this is perfectly correct, I can say Vi, j, or Vi prime, j prime. These are the two components of this animal in two different references, and it is easy to verify. We did already. You can go back to my lectures and find this calculation at the same blackboard. You can find that this is equal to Why? Because for getting Vi prime, you have Qi prime I Vi. Then you derive this animal. This matrix is constant because you are keeping two observers fixed. Okay? And the covariant index related to a partial derivative is changing in the opposite way when compared with contravariant components. Okay, so the reasoning we have already done proves that if you follow the definition given in standard fluid dynamics books, this of gradient of V, this gradient indeed is independent of the observer, which doesn't mean that two observers are estimating the same numbers. The numbers estimated by one observer are transformed into the numbers estimated by the other observer as a one-time contravariant and one-time covariant tensor should change. Okay? So you have a wonderful law of variance. Okay? Then, reasoning alla Feynman, you can say that grad V is this or that, and so you find something, this very puzzling statement. They write an equation like this, and under they say, therefore the gradient is the same vector, without explaining you why. If in your head you are like Plutarch reading Archimedes without understanding all the definitions because they were erased, not copied, because I want to simplify the book. Okay, and you are endowed with a strong sense of reality. You immediately say these people are crazy. They are the same, and they write an equation in which they are not the same. What is the wrong point of view? The wrong point of view is confusing the components with a more abstract object, which is component independent. So now I try to give you this more general component independent concept so you can give a meaning to the words which are copied under the wrong formulas. Okay? Okay. In a vector space, you can talk about, actually we are not living in a vector space. Three-dimensional Euclidean space is an affine linear space, which is an object which is a little bit more complicated, but this object has been taught to every secondary school student since the 3rd century before Christ until 10 years ago, when somebody decided that as a method of teaching was very successful, then it had to be changed. Okay, we have transformed our universe using the ideas from Euclid, then we stop teaching them. You have to think about three-dimensional space of positions are your main intellectual tool for understanding reality. You have to distinguish between points and displacements. A point is a location of a physical object having very small dimensions. And a displacement is an arrow which allows you to move from one point to the other. Of course, these are words. An affine Euclidean space is a set of points, a vector space, and a sum. The operation now is rather interesting. You have a point P. You are summing to this point a displacement, and you fall on another point. So mathematicians say that this is an external operation. Okay. I remember Davide Spinello, who came to me after a lecture and told me, "You are doing a mess." I said, "Why?" I had written P in terms of the displacement vector from the origin of an observer. And I was trying to sell this as the operation between one vector plus one vector equal another vector. I don't know if Davide had read this elsewhere or not. But what is astonishing is that his face was very disturbed. The physical interpretation of objects is essential in this story. So, 2 locations in space are something. The displacement from one location to another location is another object with completely different properties, and we need to distinguish between them. And this was Euclidean geometry as taught to students for 1,000 years. Of course, you can represent this operation in components, but in this moment, I do not want to do it. Okay? Of course, you need to tell that from every point you can go to every other point and back. Okay? So you have what we can call a flat Euclidean three-dimensional space. So why I need this? I need this because grad V is what we need to give a meaning to this Taylor expansion truncated at the first order. Of course, this means limit of W norm tending to 0 So I give you the meaning of everything. X is a position. W is a displacement. V is a vector living in the same space of displacements, because velocities are a kind of displacement in our discussion. Okay? So this difference is itself a vector. I am writing that this vector is equal to a linear map defined in V, having values in V, applied to W, plus another vector whose norm tends to 0 quicker than the norm of W. So this is the reformulation in our situation of the Taylor expansion truncated at the first order. Okay? Now, one can define the gradient of a vector field in the Euclidean space as follows. The gradient of the vector field V in the point X is that linear map which verifies this equality. Did I say something about the observer? Did I introduce a basis in V? Nothing. Okay. Now, what we can prove, starting from this obvious definition, is the following. If this Lx exists, then it is unique. So you cannot have more than one gradient in one point. First. Second, choose an orthonormal basis, represent this equality in terms of components. Which are the components of Lx? Ooh la la, exactly Vi, j. So, the linear map Lx from V to V, once you have introduced a basis in V, this linear map is represented with a one-time contravariant, one-time covariant tensor. I repeat, only if the coordinates are orthonormal and always the same basis in all different point x's. Otherwise, for you it becomes a nightmare to introduce spherical coordinates. Okay, and indeed, it was a nightmare for many students. Okay, only if you have the same basis for V in every point x, then this linear application is represented by V, J. Otherwise, you have wonderful formulas due to Ricci, Levi-Civita, which need the introduction of Christoffel symbols. Okay? Which is not a complicated subject, but in this moment it is better that we take apart this subject. Okay. So now our problem is so the step.
No.
Ok, ci sentiamo. No, ma non ti preoccupare, tagliamo. Ciao. So the next step is the following. Instead of writing this equation, we could write that epsilon d is equal to grad v, which is the tensor object represented in one reference in this way and in another reference in the other way. However, this constitutive equation must be observer independent. So the equality which we have written here can be written in this way. The constitutive equation which I want to formulate must be such that for every Q this equality holds. So you are not allowed to give the constitutive equation which you like. You cannot wake up one morning and use for epsilon d the equation which you want. Strong physical reasons require that the physically admissible constitutive equations for dissipation must verify this. Okay? Now, people are lazy and use notation in a lazy way. This is something which is talking about components. Okay? I have many difficulties to give a meaning to this equation, because grad V is an objective quantity. So I would like to avoid this notation, okay, because this is the representation of grad V as seen by an observer, and this is the representation of grad V as seen by another observer. Okay? Okay, so painfully we are now able to give a mathematical definition. I hope that I managed to give you a clear idea about the reasons for which this definition is needed. Take a scalar function defined in the set of matrices. So now we are living in the set of matrices. Phi A is a number associated to a matrix. We call isotropic function of a matrix variable. Please never believe that a variable is only a real variable x. You can have as a variable a matrix. Okay? So you need, in order to talk about dissipation, you need to introduce a function which to every matrix associates a real number. So I did all this discussion for leading you to this definition which mathematicians use as their starting point. You want to study the phenomenon of dissipation and boundary layer, dissipative boundary layers around a wing, for instance. And you want to introduce the concept of energy dissipated per unit volume in a flow of a fluid, of a dissipative fluid. So I hope that you don't believe that this is a useless subject, okay? When humanity understood this, we became able to fly. In order to talk about this, we need, and I show you in full detail, we needed step after step, we needed to reach a point, which is this one. Now, we need to study a particular class of functions. If I call M3 the set of matrices, 3 times 3, I need to introduce a function phi which to every matrix M3 associates a real number R. Okay? This application can be everything. I mean, we can invent 1,000 of these applications for 1,000 of possible physical phenomena. Okay? However, if you want to talk about dissipation in a fluid motion, you need to characterize a particular class of these functions. The function such that the level set of A includes also the matrix Q transposed A Q. Because the image phi of A is equal to phi Q transposed A Q. Okay? So we are facing with a problem which is an interesting problem between mathematical analysis and algebra. Okay. Now I try to discuss a little bit before we end this lecture about a subject which was developed by Gauss for a completely different problem, and which was used by Stokes to understanding how to postulate dissipation energy constitutive equations. I want to underline for you this. When I first started my lectures and following the tradition, as rational mechanics is not anymore taught to our students, I decided to invest 10 hours of my lectures at the beginning in order to say the essentials about rigid motion. Of course, a set of students came to me saying that all this abstract mathematics was useless. And they said there is a reason for which rational mechanics is not studied anymore. The reason is that it is useless. Okay? One of the subjects of rational mechanics was the careful study of the motion of planets. So, the problem of two bodies, of the motion of bodies around a heavier body, which could be considered the center of gravitational attraction. There are very nice equations which can be written. In particular, Kepler law tells you that the area per unit time which is spanned by a planet in the motion around the sun is constant. So we have the so-called areal velocity. Constancy, the statement, the areal velocity is constant in the motion of planets. Now, one could say, I want to design airplane wings. Why should I study the motion of planets? This is a very old objection. Sextus Empiricus, the final destroyer of Hellenistic science, was using this kind of argument, and he managed to persuade his followers that mathematics was completely useless. I'm sure that you have studied Brett formula for torsional rigidity of thin-walled beams. Okay? Brett is using exactly the formula of conservation of areas for getting torsional rigidity. Mathematics is studying logical relationships between logically defined objects. And the same structures appear in different applications. When you have a matrix A, you may define eigenvectors and eigenvalues as follows. An eigenvector of a matrix A is a triple or an n-tuple of real numbers such that A applied to U equal to lambda U for a given lambda to be chosen. So we are talking about the eigenvector U and its associated eigenvalue. Remark that we are using the German word in English. In Italian we say autovalori, autovettori. In French they say valeur propre. In English they use the German eigenvalue, eigenvector. Okay? Do you know why Gauss was using this algebraic structure? If you have an outer planet and an inner planet, the outer planet is exerting a gravitational attraction onto the inner planet. Actually, by action-reaction, the vice versa is true also. So Leverrier, using Gauss' theoretical, Leverrier was much subsequent. Gauss invented a mathematical method for describing the influence of an outer planet, of the motion of an outer planet, onto the motion of an inner planet. Leverrier used this mathematics for forecasting the existence of not yet observed planets. So he could say to astronomers, point your telescope there in this day, this hour, and you will see another planet. And this happened. Okay? Another completely useless theory for engineers, you may think. This is not true. Because if you want to find the correct constitutive equation for a dissipative fluid, you need to know the theory of Gauss about eigenvalues and eigenvectors. So once more, you may believe that something is a useless mathematical abstraction, and then you may discover that you really need to learn this mathematics. Let us move a step. I hope that you will, in the book I gave you, you find all this in detail. So please, before next lecture, try to read this, because we cannot proceed with this speed. Otherwise, our lecture will end next September, not 2013, 2014. Okay, so I need to speed up a little bit. But I hope that you already met this. So, a vector u different from 0 is said an eigenvector relatively to the eigenvalue lambda if it verifies this condition. Theorem. determinant of A minus lambda identity is equal to 0 if and only if lambda is an eigenvalue corresponding to a given eigenvector. Do you know how this equation is called? Secular equation or characteristic polynomial. Secular equation because you need to use it in order to discover the secular perturbations induced by an external planet on the motion of the internal planet. This theorem, I hope for you, is trivial because you write AU minus lambda identity U equals 0. Then you can factorize U on the right. U is different from 0, which is the rank of a matrix, which is a matrix of coefficients of an homogeneous system having non-vanishing solution. Rouchet-Capelli theorem tells you that this rank is lower than the maximum. Otherwise, you have only the vanishing solution. So in order to have the rank of A minus lambda identity smaller than the maximum, the determinant has to be 0. Okay. Now we use the last minutes of this lecture for stating a theorem about eigenvectors and eigenvalues of symmetric matrices, which we will need many times. This theorem is true in Rn, but we will apply it in R3. But the demonstration, okay, we can try to do this. Do this self-examination test. Please tell me next time, yes, we have read the theorem, we understood all steps of demonstration, we control this subject. Okay? If not, we must talk. Okay? If you remember, the transposed of a linear map and a matrix is producing a linear map verifies this condition. If the application, as in this case, is a linear map from a vector space into itself, you remember the transposed was doing a reverse travel if the two spaces are different. If you have a linear map from V1 to V2, the transposed, once you have introduced an inner product, is traveling from V2 to V1. But if V1 and V2 are the same, then the transposed is a linear map between V and V again, and there is no problem. Okay? So you can talk in this particular case about symmetry. A symmetric matrix is such that it is equal to its transposed. Okay? Okay. The very beautiful theorem, which can be proven, and if you have troubles, we will prove here, because it is essential. Whatever you will do in your life, including the structural engineer designing buildings, this theorem is crucial in everything you may do. It is always possible to find n, E1, E2, En, lambda 1, lambda 2, lambda n vectors and n scalar. N vectors forming a basis for Rn. So linear independent, such that each of these E1, E2, En is an eigenvector for the symmetric matrix A, and the corresponding eigenvalue is lambda with the same index. So you can always find a basis of eigenvectors for a given symmetric matrix. We will see that this has a dramatic consequences on the structure of isotropic scalar functions. Okay? Okay, thanks a lot.